Hello everyone, I am Dhara Kansara. Today I will discuss asynchronous down counter, up down counter and BCD ripple counter in this video. So I will cover the following content. First, that is asynchronous or ripple or binary down counter. Then we'll discuss asynchronous up down counter, then BCD ripple counter, and then we will see advantages, disadvantages, and applications of asynchronous counters. So as I have discussed in previous video of asynchronous up counter, that what is the difference between asynchronous and synchronous counter, what is the up counter. Okay, so I will just give you a reminder that in asynchronous counter, the output of one flip-flop will be given to the next flip-flop to clock pulse. And in synchronous counter, we will give clock pulse to all the flip-flops simultaneously. Fine. Now we will see down counter. What is the difference between up counter and down counter? Up counter will count from 0, 1, 2, 3 up to 7. But here in down counting, it will start counting from 7. Down counting 7, 6, 5 up to 0. Then again flip-flop will reset and start counting from 1, 1, 1. Okay, so here what is the difference between these circuits? You can see here in this 3-bit down counter, what we are doing, output we are going to take from complement of this output. I mean, I am applying clock from Q and output I am taking from Q bar terminal. But in the previous one, in up counter, what we did, we are taking output from Q and same Q I am applying to the clock. But in down counting, what I will do, I will give this output to clock pulse and I am taking output from its complement. Why I am doing like this? Because down counting means initially suppose this flip-flop will be 0, 0, 0. So Q bar will be 1, 1, 1. Right? All the flip-flop output will be 1, 1, 1. Output of this flip-flop will change its state. Will change the state of the next flip-flop. Okay, because this is what? Negative edge trigger. So in this figure, you can see this is the clock pulse, first clock pulse applying to JK flip-flop 1. This negative edge will change the output QA. Okay, this output will change its state at negative edge. Then this QA bar means whenever this QA I am applying to clock pulse and and output I am taking from this Q bar. So what is Q bar? This is exactly opposite to QA. Okay, so this is what? Output, and this is what? Clock signal to the next flip-flop. Okay, so here you can see this is what? Output. Okay, QA bar, QB bar and QC bar is the output. So counting will start from 1, 1, 1. The next count will be 0, 1, 1 means that is 6. Then 1, 0, 1 that is 5, like this way. So 7, 6, 5, 4, 3, 2, 1, 0. Then again it will start from 7. So this is what? 3-bit down counter. Okay, one more important point I want to discuss, and that is, suppose you are applying Q bar, this Q bar to this clock pulse, then you must have to take output from Q terminal, from this terminals. Here what we are doing, I am applying this Q2 clock pulse and output I am taking from Q bar. But now, suppose you want to give this Q bar to clock pulse, then you must have to take output Q from this terminal. I mean, from this Q, we will take output because this is what? Down counter. So this is what complement of this thing. Fine. Now, next we will see up down counter. So this one circuit will perform either up counter or it can perform the down counting. Okay. So this mode signal, you can see here, I am applying this mode signal. Mode signal will control this function. Means, suppose for up counting, this mode input will be connected to logic 1. And suppose I am going to use down counting, then this mode signal will be 0. So whenever M is 1, this circuit will work as up counter. Whenever this mode signal will be 0, this circuit will work as down counter. Okay. Now suppose you can see here, I am using 3-bit up down counter. That's why I have used 3 flip-flops. But some logic circuits I am using between the flip-flops. Why? Because I am using up counting as well as down counting in one circuit only. So whenever, suppose mode signal is 1, okay, you can see here this upper logic AND gate will active. You can see here, if this signal is 1, then this 1 I am giving to upper logic AND gates. So whenever mode is 1, means suppose I want this circuit to work as up counter, then I will give M is 1. So upper logic AND gates will work. This input I am giving to OR gate. So this OR gate will given to the clock pulse of the next flip-flop. So what happened actually? At the same time, I am applying this output to AND gate also. Mode signal 1, logic 1, mode signal 1, logic 1 I am applying here, and this output will be given to the AND logic. So this output I am giving to OR gate, and this will active this flip-flop. This is again negative edge. So the negative pulse means whenever it will move from 1 to 0, this will change its state. And it will start up counting, means from 0, 0, 0 to 7, 1. I mean 1, 1, 1. Counting will be up to 7. Up counting. And suppose I am going to use down counter. Then what happened? This mode signal will be 0. This 0 I am applying to this lower logic gates and gates. So what happened? This QA bar I am applying here. As I told you, if you are going to use down counter, then this QA bar I am applying here and output will be taken from here. So this QA bar I am applying here and this mode signal, that is 0, I am applying here. Accordingly, I am applying this logic to the negative edge clock pulse of the next flip-flop. So it will change its state. This flip-flop will change its state whenever this output will change its state from 1 to 0, because this is negative edge trigger. Okay, like this way, all this flip-flop will change its state at its negative edge clock input, and the function will be same as we have seen in up counter and down counter. Okay, so function will be same, but here the difference is that I am going to use mode signal, and mode signal, if it is 1, then it will work as up counter. This mode signal is suppose 0, so it will start down counting. Okay, two more thing I want to tell you, that PRE and clear signal. Here I am using PRE, that is preset, and clear. CLR is clear the flip-flop. So whenever I will give, this is what PRE dash and clear dash. I mean PRE bar, CLR bar I am using. So inverter will be there inside this flip-flop. So what happened actually I am giving this signal to logic 1. Then internally it will be 0. And here similarly, so suppose I am applying CLR dash is equal to 1, then internally it will be 0. Means suppose whenever I am applying here 1, it will clear the flip-flops. Okay. So suppose I am going to use this circuit as up counter. Means counting must be start from 0, 0, 0. So initially I will clear the flip-flop. That's why it will count from 0, 0, 0, then 0, 0, 1, then 0, 1, 0, up counting. So whenever you are going to use this circuit as up counter, so you must know two things. You have to remember two things. First, that is mode signal. Mode signal must be 1. And the second thing, this preset signal must be 0 and clear signal also must be 0. Means it will clear the flip-flop. Counting will start from 0, 0, 0. But suppose if you are going to use this circuit as down counter, then what I will do? I will give 1, 1, 1 initially. So preset means previously I will set this flip-flop to 1, 1, 1, to logic 1, 1, 1. For that I will use preset input. So if I will give here 0, so 0 bar will becomes 1, right? So 1, 1, 1, then it will start from, counting will start from 1, 1, 1, then 1, 1, 0 means 7, 6, 5, down counting. Okay, so you must know all these things. Whenever up counting means this signal must be 1, clear to 0, and mode signal to 1. Whenever you are using down counting, then this signal is 1, preset signal must be 0, and mode signal must be 0. So this common circuit you can use as either down counter or up counter. Okay. This is the truth table. Whenever, as I told you, this same circuit will work as a up counter and down counter. Up counter count start from 0, 1 to 7 and down counting 7, 6 to up to 0. So this is what truth table of this. Okay, then we'll see another type, that is BCD ripple counter. BCD means, you know, binary coded decimal. Okay, valid binary number up to 9. So counting will start from 0 and end with 9 because valid BCD number is 9. So flip-flop will reset from 10. That's why name is decade counter also. This ripple counter also, BCD ripple counter also known as decade counter. Okay, because 0 to 9 means 10 count will be there and it will reset from 10. So this is known as decade counter also. So as you know, the 9 decimal number, 9 is decimal number and binary equivalent is 1001. Means we are using 4 bits. So 4 flip-flop I will use. So this is the circuit. 4 flip-flops we will use. These are the JK flip-flops, and I want to design circuit like this way. This is the 4 flip-flop. So logically, it will start counting from 0, 0, 0, 0, and it will stop at 1, 1, 1, 1. But in the BCD counter, I want to stop at 1, 0, 0, 1. So I will design this circuit in such a way that after count 1, 0, 0, 1, it will reset the flip-flop. Means then it will start counting from 0, 0, 0, 0. Okay, that's why there is a slight difference compared to other counter circuit. And what is that? You can see here, I am applying the JK to logic 1. But at this flip-flop, I mean the second flip-flop and the last flip-flop, what I am doing, I am giving this Q2 and Q4 to this AND gate, and the output of the AND gate will be given to this J. Why? Because as I told you, I want to reset this circuit at 1001. So this is what state diagram. Counting is starting from 0000 and will end up at 1001. So 1001, then I am applying this output in such a way, it will give next state 0, 0, 0, 0. Because as I told you, whenever this is 1, 0, 0, 1. So this is what 1, and this 1 I am applying here. But this is what 1, 0, 0, 1. So whenever this Q8 is 1, this complement output is 0. I am applying here 0. So 0 and this I am applying to 1. So 0, 1 means it will reset the flip-flop. So this flip-flop will be reset because I am applying here 0, 1. If this flip-flop is reset, means this 0 I am applying here. AND gate, any input is 0, output will be 0. Again here 0, 1. So it will reset this flip-flop. So I am getting here 0. Are you getting my point? Similarly, I am applying this 0 here. Okay, so now you can see here, we'll get 0, 0, 0, 0. So simply, by this logic operation, we will reset the circuit after count 1, 0, 0, 1. So simply, this is known as BCD ripple counter. Suppose I want to use more number of decade counters. So we will use separate BCD counter. Suppose I am going to use for 10 raised to 0 means first digit from unit place. I will use one BCD counter. For second place means 10th place, I will use another counter. Then for 100th place, I will use third counter. I will use 3 different BCD counters for 3 different digits. Okay. Now, what are the advantage of asynchronous counters? We can use truncated counters. Means truncated counters means what? We can change the states of the counter. Suppose, as I told you, I am using suppose 4-bit counter. I'm going to use 4-bit counter. So counting will start from 0, 0, 0 up to 1, 1, 1, 1. But I want suppose counting up to 10. So I will design the asynchronous counter in such a way that I can get counting from 0, 0, 0 up to 10. So this is what truncated counter, modulo or divide by n counter. So we can design the circuits by using this asynchronous counter. But what is the disadvantage? We suppose we are using this divide by n counter, then we require extra feedback logic circuit. So this is again the disadvantage, because we want more logic circuits to give. Okay. And suppose counting a large number of bits, then propagation delay by successive stages may become undesirably large. So propagation delay is again disadvantage. This is what applications of asynchronous counters. As I told you, we can design mode 3, mode 4, mode 8. Means whatever count we need, we can design the counter like this way. Then we can design decade counter by using this asynchronous counter. Then we can use these counters in frequency dividers, frequency counting circuits, or else we can use these circuits in state machines also, in clock generation, clock division also, right? So these are the applications of the counters. Okay, students, thank you.